Thank you very much for having me and for the kind introduction. I mean, I already mentioned this to Card. I would have, of course, come in person, but we're expecting our first child at the moment, and so I wanted to make sure that I'm actually there for the birth. So we've got some materials to cover, and like Kathleen, I would suggest that you just interrupt me while I'm talking, since I can't actually see the chat very well at this point, and so I'll try to keep it on the level of an interesting introduction to these two topics, namely geometry and topology in machine learning. Now, let's start a little bit with the preliminaries. I don't think there's a lot I have to say about geometry as a motivational part in this talk, because it is generally accepted to be useful in machine learning. We deal with point clouds, and we deal with images, and we try to extract some kind of features from them, and it's generally accepted that this is a good thing to do. I totally agree with this. And indeed, I would say that geometry is great at capturing fine-scale information about the data. So if you want something very fine-grained, very, very fine details, then geometry is the way to go. What I'm trying to do a little bit in my research and also in this talk is to convince you that topology, the, let's say, opposite side of geometry, is also of use. And here I would say that topology is great at providing qualitative answers when quantitative answers are either too complex or even impossible to give. So the classical example is if you want to travel from some place on the world to some other place on the world, if we kind of know where these places are, then we know that you might have to cross the equator at some point, but depending on the actual itinerary that you take, we might not know where this place is. So this gives you a great way to understand what type of questions we might answer with topology. Now, the famous example that I really like for emphasizing what topology can do for you dates back to Euler, and is the 7 bridges of Königsberg, where the idea is, can we have a walk through the city that crosses every bridge exactly once? Now, the main ingredient of this problem is also to translate the geometry into a topological structure, into a simpler structure, and answer this qualitative question. Because we don't care about the length of the walk, we don't care about the actual itinerary, we just care about the fact that this walk has a certain property. And thus we translate this problem into a graph where the bridges are being connected if we can reach them. And then we find that no such walk can exist because there are more than 2 vertices in this graph with an odd degree. So you have to go in and out. And so therefore this doesn't work out. This is a very simple, but I think very compelling example of the power of the topological perspective. But of course, we want to do more. We want to do this with data, right? So what we're looking for in data when we're dealing with complicated topological objects is to assign them simple invariants. An invariant being a characteristic property that doesn't change under certain transformations. So for instance, under homeomorphism. So if we have 2 spaces and we stretch them and bend them, but we don't cut them, then these invariants should typically remain the same. You can have stronger invariants or weaker invariants, right? But fundamentally, that's what it boils down to. And a very simple invariant is given by the Betti numbers of a space, which informally people always say this counts the number of d-dimensional holes. And so you can use that to distinguish between different spaces. In dimension 0, you have the connected components. In dimension 1, you have the cycles. And in dimension 2, you have the voids. And if we tabulate that a little bit, we can see that this kind of corresponds to our intuition. A point has almost nothing except for a connected component. A cube is a little bit more complicated. A sphere looks like a cube with respect to that invariant, of course, right? Its geometry is different, but topologically speaking, in terms of holes, it is the same. And then we have the torus as something different. Namely the number of loops, non-trivial loops in dimension 1 is a little bit striking. To briefly illustrate that here, this is what happens. We have 2 non-trivial loops that we can prescribe on the surface of the torus. And so since this differs for the sphere and the torus, we also know, since this is an invariant, that the 2 objects cannot be homeomorphic. Now, this is all well and good because, well, we can distinguish between those 2 classes of objects, but in practice, life is a little bit more complicated, or I should say reality is often a little bit messy. So instead of having this nice platonic object as the torus itself, we just get this torus point cloud here. And then we have to make do with assigning this somehow this platonic object. And this is what novel technologies from computational topology including the leading flagship algorithm of computational topology, namely persistent homology, is all about. So persistent homology has the idea that you track topological features across different scales in the data, and you do this by approximating your point cloud at different scales and observe how features appear and disappear as you change the scale. So this is illustrated here. Simply, we build a complex based on pairwise distances, and we let this complex grow. And at certain scales, at certain connectivity scales, we observe that we now have this red cycle here. It persists for a while in this scale until at some point it is being swallowed by the remaining complex because everything is now closed off. And this fundamental concept also works, of course, for the more complicated point clouds like these persistent, like the torus that we saw before. And it's a fundamental, nice algebraic process that takes a space and associates a so-called persistence diagram to that space. So we again see the growth here. We can do this over all the scales. And then at the end of this growth process, we have a sequence of persistence diagrams, of these diagrams on the right-hand side that describe the topological features and the topological activity in this point cloud at multiple scales. You have to think about this intuitively from the point of view of saying that a certain topological feature might be created for a certain scale, and then it might disappear for a certain other scale. And this, I should say, is a generic way of associating a sequence of these type of diagrams to certain objects. And we can do this with a variety of different data sets or data domains in some sense. Namely, we can do this with graphs, we can do this with point clouds, and we can even do this with time series if we want. So this is a very concrete implementation of a very generic way of dealing with data. Now, I don't want to go into the proof details here, of course, but computational topologists like this method specifically because you can also have distances between those persistence diagrams. So you get a proxy way of looking at your data by projecting it essentially into this space of topological features. You get ways to then compare your objects in this topological representation. There are two interesting distances. They're very much related. The computational details are not super important, but they're both based on optimal transport or optimal matchings. So we take the points in one diagram, we try to match them in an optimized manner to the points in the other diagram. And then we either do this in an infimum way or we do it in a kind of averaging way. And this leads respectively to the bottleneck distance or the Wasserstein distance. And the great thing about this, and this is a kind of an intuitive view, is that the process of generating persistence diagrams, of generating these descriptors from point clouds is stable in a very concrete sense. By stability, we mean that if we change the point cloud a little bit, for instance, if we subsample it or if we wiggle the point positions a little bit, the diagram changes continuously with respect to the distance between persistence diagrams. So more concretely, this means that if we have a triangular little space with continuous tame functions, this is a very technical detail, but it's always in practice satisfied except for very degenerate cases, then the corresponding persistence diagrams satisfy that their topological variation on the left-hand side is upper bounded by the geometrical variation or by the functional variation between the two functions on the right-hand side. So that to me is a remarkable result because on the left-hand side, we have topology and on the right-hand side, we have geometry of the data. And this, I would say, forms the basis for why people like to deal with this type of framework and why they use it in practice. Now, in the context of machine learning, my group and my colleagues have been doing some great work here. We have a bunch of interesting threads open at the moment, and I will not be able to zoom into all of these, but we have used topological features as a way to institute an additional set of inductive biases to a model, so making sure that the right representations are being learned and so on. We also use them to complement machine learning algorithms, so to learn things that cannot otherwise be leveraged. And I'll be showing an example of this in a couple of slides. But we also were able to show that there are some advantageous theoretical properties of these features in the sense of these features increase the theoretical and empirical expressivity of our models in a certain precise way. So we can distinguish between different classes of objects and so on and so forth. Now, the generic topology-driven machine learning pipeline that you will often find is that people start with one of these point clouds. They use the persistent homology algorithm as a way to grind through the data to create some kind of new representation from it. This then gives a set of persistence diagrams that are then subsequently fed to a machine learning classifier. And that is not a bad pipeline, but it is a very restrictive pipeline in the sense that it doesn't make use of all the capabilities of machine learning algorithms, namely the primary capability of learning task-specific representations in a differentiable or in a somehow continuous manner. And the crucial insight that can be found in our work and in the work of others is that it is indeed possible to what machine learners call backpropagate information through this pipeline. That is, there is a gradient essentially from the machine learning algorithm back to the persistent homology calculation under certain mild conditions, such as unique distances and things like this. And we have been using this type of construction for quite some interesting things over the past couple of years. For instance, we have a topology-based loss term out there that adjusts to the data topology and makes it possible to learn latent spaces that are more in accordance with an input data set. So the point I want to make is that it is possible to use topology and topological features as kind of static features that enrich a machine learning task, but you can also embed and integrate them directly and make them first-class citizens in some sense and make everything differentiable under certain mild conditions. Now, let me show an example of how to use topological features in practice. And this is a little bit unusual in the sense that it doesn't make use of deep learning models as such, but rather it gives you a way to create new insights into your data. And with this, I want to lead you on a brief journey in this work, which was done with my awesome student Julius. It just appeared at ICML. It's called Topological Singularity Detection at Multiple Scales, and you can check out the paper and the archive preprint and so on, also on our website. The central premise of this work is that we say most methods assume that your underlying data has a very nice manifold structure. So that is, we assume that we have some kind of unknown manifold and the data we observe are kind of sampled from that manifold. But reality, as I already said before, is often a little bit messy. So the question is, can we detect deviations from such a structure? So can we detect what happens when these assumptions no longer hold in practice? And this is where our work comes in. It's this is kind of the, let's say, cartoony justification for this. So we know that a d-dimensional manifold is a space that is maybe locally homeomorphic to some kind of d-dimensional real valued space. So every point behaves the same or is very uniform. But and this is very good because it simplifies data analysis, but I always have the feeling that putting everything into the manifold learning framework is like pretending that everything in the world is just this kind of flat white bread, when in reality, real data comes in many different forms. And maybe I should even show some kind of half-eaten bread here or something like this to really drive the point home. But anyway, it's clear that we need some additional views and some additional perspectives on the data. And the main intuition that drives our method is a very simple one, namely that we can actually detect to what extent a data set deviates from a manifold by just looking at its neighborhoods, or let's say looking at its punctured neighborhoods to be more precise. So this is a very simple example of a non-manifold data set. It's a figure 8 curve, and technically, if it was a circle, then it would be a nice one-dimensional manifold, right? No questions there. But because of this intersection point in the middle, we have at least one singularity there. And we can detect this by zooming in and removing a small slice from the manifold. From the data. It's of course not a manifold. So you can see that the point X, if we remove some slices from there, including X itself, we can see that it has a regular neighborhood. It consists of two connected components. So we have this one part of the data and the other part of the data. The rest is kind of removed. So this is an annulus construction. And if we look at the other point, however, at the point Y, we can see that it has an irregular structure. So at all the other points of this figure 8 curve, we can do this construction and we can calculate the neighborhoods, but only for the point y, this doesn't work in the end. So that's the main observation that drives everything. And how do we leverage this in practice? Well, we leverage something that we call persistent local homology. Well, not only we call it that, it exists before. So we're standing on the shoulders of giants here, but so I don't want to pretend that we are inventing all of this. But the idea is that we take a small neighborhood from our data, so from this torus again, right? We construct an annulus being something like the equivalent of a punctured neighborhood, and then we calculate the persistent homology of this annulus. And this gives us a way to compare the annulus with an annulus that we sample from Euclidean space. So essentially, we do this in a completely data-driven way. We go into the data, we sample our points, and then we compare the resulting topological structure to the resulting topological structure that we would have in a nicely Euclidean space. And since, if you recall from the beginning, since there are well-defined distances between those topological descriptors, this indeed gives us some way to assess the deviation of our data locally from the Euclidean model space. Now, it's a little bit, I'm glossing over a lot of details here. Of course, this is not very simple to obtain in practice, but the main algorithm is based on growing this intrinsic annulus around a point and then adjusting the parameters accordingly. So if you're already in the know a little bit here, this leads to a so-called tri-filtration of the data. Now, where can we use this? Let me give you an example. This is something that I care about because we're trying to look into new kinds of life sciences examples, and we try to figure out whether high-dimensional embeddings actually make sense for these data sets. And of course, since this is an unsupervised task, this is not really easy to solve. And here we have a very simple cytometry data set. So I don't want to pretend that I understand all the details of how this data set came to be, but what I do understand is that it depicts certain cell types and how they diverge and split according to different lineages. So there's literally a how can I say that, a kind of agglomeration or accumulation of different time snapshots of the cells and how they develop over this period. Now, the important thing is that we already know that this data set, according to biology, according to biological knowledge, needs to contain and depict certain branches in the data because the cells need to split up and go into different things, right? And with our method, which we call Euclidicity, because it measures the deviation from Euclidean space, we obtain a nice complementary view on the data. So we can basically calculate this on the original space and then overlay it on top of different dimensionality reduction algorithms and see whether certain parts of the data have been nicely retained. So picture says more than 1,000 words. So let's take a look at what this says. And indeed, you can see that we get this branching structure in our unsupervised dimensionality reduction algorithm. And when we overlay this with the Euclidicity values that we calculate on the original data set, we can see that there are some large deviations from Euclidean space. Indeed, during the time where these cells start to diverge and where they start to split into different lineages, whereas the endpoints of the cell, so where they then actually land once they have developed, those are relatively low. Those have relatively low Euclidicity, meaning that they are captured rather well by a normal Euclidean space. And this is just, in some sense, a little bit of a teaser of what one can do with this method, but we found it very, very important to kind of open up this discussion in the machine learning community about going beyond manifold data and imbuing your neural networks and your other models with a little bit more knowledge about these type of singularities that exist in the data. Now, that's one facet of the talk. I now want to briefly switch gears and talk a little bit about curvature. But before we do that, maybe give me an understanding of whether there are any questions so far in the chat. I didn't see anything.
No. Can you hear me? Can you hear me?
Yes.
That's not a naive question. Even if the manifold hypothesis is not met, does it make sense to make an estimate of dimensionality or latent dimension of a data set?
Yeah, I'm not sure whether I caught all of this, but I think the so I would say the manifold hypothesis might of course make sense. But what it doesn't handle, for instance, is it doesn't give you a way to assess the changes in dimensionality. So even if you assume that you have a manifold, it's still important to understand whether certain parts of your data might arise from different manifolds. So the manifold hypothesis doesn't necessarily cover constructions like the union of different manifolds, even if they're just disjointly union, right? This is all not covered. I hope I got that correctly. Right, very nice. Are there any other questions? Oh, now I'm seeing something plop up. Let me click on that and let's see what happens. Wait, where's the? Let's see where the chat window now went. Okay, it's not shown on my screen. Wait a second. Yeah, I need to get this chat window open again, but I think it should. No, I'm sorry. Apparently I can only see the either the screen or the chat, but not both.
Bastian, don't worry. I made the question. I can repeat it aloud if you want. Yeah, my question was like, if there is some kind of topological structure, geometrical structure that is better suited to represent real data, more suited than data that manifolds.
Yes, I think one important representation would already be kind of just the union of manifolds or an intersection or something like this. So if you have an understanding of how these manifolds are behaving in your data, then you can also partition your space accordingly and maybe treat each part of that space with a different type of algorithm, for instance, right? So it's not so much I don't want to say that the manifold hypothesis is useless, because of course it's not. It's more a question of detecting these deviations at some scales in the data so that you can handle them accordingly with your algorithm. Does that make kind of sense?
A lot. Thank you very much.
Okay, great. Thank you. Then if there are no other questions, then I'll move on to the curvature part and hope that this is not something that everyone knows. But I find curvature a very compelling topic, and topology will come up again soon, I promise. I find it compelling because it can kind of combine different geometrical and topological aspects of the data. Intuitively, and this is something that I found very distracting in the beginning when looking into this topic, is that there are so many different ways to define curvature, but all of them are characterized by the idea that you want to see how curved an object is, right? Like a surface or a manifold or something like this. You can have extrinsic or intrinsic curvature. We are mostly interested in intrinsic curvature, so something that doesn't depend on a specific embedding, because we want to characterize data as standing on their own, right? Without relying on a specific embedding. Simple example of this is the Gaussian curvature, which is the product of the principal curvatures. I don't want to go into the details of how these are being calculated, but I do want to show you three prototypical spaces that will crop up again. Namely, we have a hyperbolic space, which looks a little bit like a saddle of a horse. This is negative curvature. We have a flat Euclidean plane, which is, of course, zero curvature or flat curvature, if you will, and we have a positively curved space, which is a sphere. So these are kind of the quintessential model spaces of Gaussian curvature and of other curvature values as well. Now, another way to characterize curvature that is often alluded to is the idea that in negative curvature, your geodesic triangles that you have on the surface, they are kind of thinner than reference triangles, so they exhibit angular defects. You can see this by drawing this kind of hyperbolic triangle, this kind of geodesic triangle on a hyperbolic surface, and you can see that the angles start to become weirdly defective. Now, positive curvature, on the other hand, this is I think the thing we should care about the most for various reasons that will become clear subsequently, is that in positive curvature, or rather I should say in positive Ricci curvature, if you have corresponding points or spheres, then they are closer than their respective centers are. So corresponding meaning that you do parallel transport. I don't want to go into the specifics here, but I do want to show you an intuitive view of this problem. So if you're in a flat space, there's nothing to do, right? You are in your flat space, you draw your spheres, and then you just pick a point. You pick a corresponding point, so something that is at the same level, at the same distance of your starting point. And nothing changes. However, if you are on a positively curved space, and now you have to believe me that this is supposed to be positively curved, then you can see that the geodesic between those 2 points, those 2 corresponding points here, becomes closer than the geodesic between those centers. So that's a consequence of the curvature. It's a little bit hard to illustrate this for me, and this is the best I could do. If you have some ideas of how to do it better, then please let me know. But that's kind of the rough idea. So we measure whether corresponding points are closer than their centers are. And this is indeed useful because many curvature measures satisfy a very nice characterization of the space and kind of combine topology and geometry in very deep ways. And I hope I can allude to some of these properties here. So one of the things that I found fascinating is that despite being a local quantity, curvature itself provides information about the global characteristics of a manifold. So we have the famous Gauss-Bonnet theorem, which basically means that if you integrate curvature over the manifold and over its boundary, you can use it to get the Euler characteristic of the manifold. And at least for me, that was a surprise, because the Euler characteristic is a purely topological property, while curvature is of course not, right? So you can already see this kind of deep links here. It goes even further. You can have a Bonnet-Myers type of theorem, which tells you that if you have an upper bound of your curvature of your manifold by a sphere, then you know that the diameter is also upper bounded by this. Oh, sorry, you have a lower bound and then you have an upper bound in terms of the diameter, and you know something about compactness. So that again tells you something about the geometrical characterizations of your data through curvature. And I think it's an important thing to keep in mind, and we'll come back to this, of course. Now, in graphs, and this is what I care about the most at this point, curvature is a little bit harder to define because mostly we're not dealing with the smooth space. So the only thing that we will be assuming now, once we get to define some concepts, is that we need this graph to be connected. But other than that, we can do it in all settings. And before we go into the specifics of defining curvature for graphs, let me first give you an outline of how colleagues have used curvature to characterize certain things in machine learning research. So it turns out that graph curvature actually explains certain problems in training graph neural networks. In particular, negative curvature turns out to correspond to bottlenecks in the information processing, also known as as well as the over-squashing phenomenon, or in general bottleneck phenomena, which make training a graph neural network on this type of data a little bit harder to do. There's great work by Topping and colleagues, it was recently revisited and extended to other notions of curvature by Nguyen and colleagues. So check those out if you're interested in them. From my end, I have some research to contribute to this direction as well. Namely, we were recently able, in an iClear paper, we were able to show that we can use graph curvature as a characteristic property for simplifying certain graph learning tasks, well, more specifically hypergraph learning tasks, or we can use it to compare different graph generative models, which is the preprint that I will show you later on. Now, to define curvature on a graph, there is a lot of additional notions that we could use, but the one that I like the most for different reasons is the Olivier-Ricci curvature. So Olivier-Ricci curvature is based on very simple ingredients, namely you need a shortest path metric on your graph, and you need probability measures on each node. And then if you have those two ingredients, you can define the Olivier-Ricci curvature for any pair of nodes ij by using 1 minus the Wasserstein distance between the corresponding probability measures divided by the distance between the two nodes. Hence, this is because of this division. This is the reason why we require the graphs to be connected. The Wasserstein distance is, of course, an optimal transport distance that tells you something about the amount of work you have to do to transform one of the probability measures into the other one. And in some sense, this measures is the natural generalization of Ricci curvature to a larger class of objects, because it contains this idea that you take the corresponding points, so you take the points that you find in a small neighborhood measured by a probability measure of your node, and you see how whether those are closer or whether those are further apart than the geodesic between the points describes. This was first introduced by Olivier, actually for metric measure spaces, but it was quickly adopted and adapted actually for use in the setting of graphs, because it's extremely convenient and very nice to calculate. There's also, I'm going to gloss over these details, to be honest, because I don't think they're super important here, but I just want to say there are some nice properties like lower bounds, so you only have to calculate this for the edges, and there is a Bonnet-Myers-like theorem, meaning that you can bound the diameter of your graph with this. Furthermore, there is a kind of, let's say, canonical choice. Actually, it's not canonical. Maybe I don't want to be recorded saying this, but there is a certain common choice for the probability measure. So basically, people define the probability measure based on lazy random walks. You take a laziness parameter. You either stay at your vertex, or you distribute the rest of the probability mass to your one-hop neighbors. If you have this, you get very nice bounds for the Olivier-Ricci curvature on the graph. And again, you even get a nice Bonnet-Myers theorem. But in theory, you could use other probability measures, and we'll later on see how that makes sense. The important thing for you to take away from Olivier-Ricci curvature and to kind of memorize this concept is that there are some canonical examples of this notion of curvature. Namely, you have negative curvature, which corresponds to more of these tree-like structures. Flat curvature corresponds to more grid-like structures that are very regular in a sense. And positive curvature corresponds to extreme clique-like or even complete graphs. This is a great figure inspired by paper by Devrion and Lambiot on discrete curvature on graphs from the effective resistance. Also very well worth a read if you're interested in curvature. Now, as the last application, I want to show you how to use curvature to compare graph generative models. And this is where we throw everything that we heard before, all the geometrical and topological concepts together, and see what we can do with that. The main problem that we want to address in this work is that if we have a distribution of graphs and different models for generating new graphs, how close or similar in the distributional sense are these two distributions then? So can we say something about a model being able to provide realistic graphs? That's a very important problem for various domains. For instance, if you want to generate realistic graphs, or if you want to generate molecules that have certain properties and so on. And we want to address this by a topology and geometry-based method. This is joint work with Josh and Jeremy and Michael Bronstein. And the central premise is that we believe that since curvature is a multi-scale phenomenon, so it tells you something about the local and the global properties of a graph, so we also need descriptors that are inherently capable of leveraging this multi-scale structure of a graph. And to do this, we borrow some ideas from persistent homology and use the curvature as a so-called filtration function of the graph. I haven't introduced this concept in full practicality yet, but if you recall what we did for the point cloud example, where we let some Euclidean spheres or Euclidean balls grow and characterize the connectivity of the resulting point cloud, we can do the same thing if we have curvature on the graph nodes and graph edges. The only difference is that the scales that we look at are now dictated by the curvature function, but we can still look at all the topological features that occur in graphs. And in fact, this setting will make it even easier to do this, which we will see in a second. So we take our persistence diagrams that we calculate based on this curvature filtration. So we get topological descriptors based on curvature. we convert them into more suitable representations. The algorithmic details don't matter here, but we have them outlined, of course, in the preprint, and we also explain why these representations are more suitable. And then we can compare those representations using permutation tests, averages, or distances. And that gives us a very nice and foundational way to compare the overall distributions arising from the graphs without having to resort to some kind of other embeddings or other calculations in terms of something like a maximum mean discrepancy, for instance. Now, a simple example of how this filtration looks in practice, if you consider this to be your graph, then we look at essentially the pre-images arising from filtering over different levels of this of the curvature values here. And since we're just dealing with the graph, we have it a little bit easier here because we only get connected components and cycles. These are the only two types of topological features that we're currently capturing. We could capture more. There's a whole theory around it. We could capture cliques and so on and so forth. But we wanted to keep the initial prototype very simple and also very computationally effective. And for deep reasons that I can't go into, unfortunately, the calculation of topological features in dimensions 0 and 1, so connected components and cycles, is very, very efficient to do. In any case, we get these multi-scale topological descriptors known as persistence diagrams, and we then can compare them. And now here you have to take something on faith that I tell you, because I can't go into the algorithmic details, but if you recall what I said in the beginning, you can easily get a type of metric between persistence diagrams. So persistence diagrams form a nice metric space, but what we want to have, since we want to do statistics on them, is we want to have a type of Banach space representation and some statistical analysis. And so we rather transform these persistence diagrams into different descriptors. In our case, Betti curves or persistence landscapes, for those of you that have heard about them. If you don't have heard about them, that's no problem. Just think of this as mapping them into another space that allows statistical calculations. And this already brings me actually to the results of what we can do with this, because one of the things that we observed here is that already the curvature on its own is very expressive. It's a very expressive property or invariant of a graph. We use this to distinguish between different types of graphs that we know to be non-isomorphic, and we check whether other methods can also do the same. And in this data set, this is a data set known as the Breck data set, which was specifically designed to make the comparison of graph expressivity a little bit harder in practice. So there's a couple of baselines that cannot distinguish any of those graphs. So you can see that the so-called one-dimensional WL test has essentially zero chance of classifying those, but curvature does it a little bit better, depending on the probability measure that is being used. So for instance, we are quite good at distinguishing between regular graphs here if we have a random walk that goes a little bit deeper into the graph. And we're even kind of okay at distinguishing between strongly regular graphs, for instance, if we increase this measure as well. And what I do want to stress is that this is all just done based on the probability measure, going a little bit deeper into the graph and just comparing distributions. So there's no really deep neural network secret or neural network magic here, which is why this is already a very nice and astounding result that it's so expressive on its own. We, however, also put it into this curvature framework, and then we saw that curvature filtration, so the topology-based approach, is also very expressive. And indeed, we can see if we take Olivier Ricci as a filtration, we can go up to 93% from formerly 0% without topological information to distinguish between certain kinds of strongly irregular graphs. And we even found that the curvature filtrations can help in substructure counting. So they can take stock of the substructures that you have already in your graph and make this available in a nicer fashion to a classifier. Again, I want to stress that this is not done without any deep learning, but it's rather like a very nice post hoc analysis strategy. So coupling this and integrating it into a deeper neural network or into a graph neural network is bound to lead to even better results in the end. But for now, we're already very, very happy with these type of results, because this tells us that curvature filtrations together with topological descriptors are very nicely capable of distinguishing between different sets of graphs, and we look forward to using them in practice for comparing graph distributions. Now, that brings me to the end, and I want to have a couple of points for discussion before taking additional questions. So I hope that this talk showed that geometry and topology are very nice in that they offer complementary perspectives for data analysis. In particular, I want to stress that they are still useful even if the manifold hypothesis does not hold. So all the computational topology methods, they don't necessarily, some of them do, but not necessarily all of them require the manifold hypothesis to hold. So you can even apply them in different settings. Moreover, I want to stress that we believe that curvature is an expressive and useful invariant and property for graph and hypergraph learning tasks, since it also provides some kind of complementary multi-scale perspective on graphs and graph distributions. I want to stress, of course, that there are some non-canonical choices to be made here. So in particular, the choice of the probability measure, this still needs to be studied. So there's lots of additional work to be done. In particular, we need to understand whether the choices that we make in these probability measures, whether they lead to any issues, whether they limit our expressivity in a formal way. Yeah, and that's it. I hope you enjoyed this. If you like this, please also consider looking at our website or at our repositories on GitHub. So we try to have a nice presence there and discuss geometry and topology in general for machine learning tasks. But knowing my organization in the background, Helmholtz Munich and Technical University of Munich, there's always some kind of life sciences angle on there. So if you're also interested in this and you want to study complicated data from biomedicine with these type of methods, then please let me know. I would be more than happy to understand how to leverage these type of features in practice and showing that they can be indeed beneficial. So thank you very much for having me, and I hope I can take some additional questions now.
Thank you very much indeed. Let's see if there are questions either from the audience here or from the
I'm sorry, I have trouble hearing this, to be honest.
Yes, well, thank you very much for the very nice talk. My question, in fact, regards to the very nature of the interaction between geometry and topology. So in other words, you study data sets by taking advantage of by imposing specific conditions in the data themselves. And from my perspective, I have known about this suggests that you are digging out some of the features of the data set per se. And because of the limitations on the characterization we did about this, of the geometrical and topological characterization of the data set themselves. Can you comment on that a little bit?
Yeah, sorry. I was trying to get the gist of that. It was a little bit hard to understand at times, but what is the question related about the limitations of geometry and topology and topological characterizations of data?
Yes.
Okay, yeah, great. Yeah, so one thing where this doesn't work nicely is if I jump here to the topology calculation, we are kind of still bound to having a metric or a dissimilarity measure here. So if your data does not come equipped with a very nice way of assessing the similarity of the data points, then I think this is not a good way of characterizing this. This is indeed true. another limitation that we often run into practice is the missing scalability. So these methods, they are very, very bad at scaling to extremely large data sets, because you literally need to calculate all these intersections here, right? You need to figure out whether this holds for all pairwise intersections, and this creates a massive waste of spaces and requires a lot of memory. For the curvature approach, it's a little bit different. So this curvature approach, the main issue to overcome here is figuring out what type of probability measures are useful. So the community is predominantly at this point using a simple random walk-based probability measure, but I think our mini experiments already show that this is, that we can do better, at least if we go a little bit deeper into the graph, which is surprising because curvature is usually said to be a local property of the data. But it turns out that if you go a little bit more into the graph, so if you smooth out the locality, then suddenly your results become a little bit better. So, but yeah, those are two things that come to mind when it comes about the limitations. And then, of course, this also doesn't necessarily scale that well unless you have very good algorithms for solving this optimal transport problem, because you ideally, you have to do this for all pairs, right? So that's already n squared. And then you want to make sure that this can be calculated efficiently, at least, because otherwise, otherwise you're losing out on some of the computational scalability. I hope that this answered some of the questions.
Thank you.
You mentioned a couple of times graph learning. How do you feed graphs into a classifier? Do you use curvature or otherwise what?
Yeah, that's a great question. So at this point, we only use curvature to describe the graph and obtain a nice vectorial representation. So we never deal with the original graph, but we only ever feed the vectorial results, or specifically the persistence landscapes into classifiers. It would also be possible to integrate curvature directly into a deep neural network or into a graph neural network, right? But we didn't do this for now because we're not sure whether this is the right direction for better expressivity. Because if we integrate it into graph neural networks, then we are also always bound to this message passing paradigm, and it's unclear whether passing all the curvature information through the graph, whether that is not the wrong thing to do, because it might average out the information that we're looking for. So maybe we're looking for for just a few edges that have some properties in terms of curvature. And if we would feed all of those into message passing, then this information would get lost.
More questions? Here, nothing in the chat.
Let me check. Yeah.
No. Maybe one last question. Those methods, the last method that you described, they are not only for graph. You mentioned hypergraph, adaptive feedback. Does extend to higher dimensions, like kind of intuition complexes?
Yeah. So the curvature indeed extends to hypergraphs. That is something that we've been looking at in one of our recent papers. It's by far not finished, this research project, but we were able to show that there is some kind of framework that we can use to derive let's say a battery of different curvature measures for this type of modality. But then it gets much more interesting, I would say, because the effects of curvature in the, let's say, smooth setting of hypergraphs, I'm not sure whether they have been studied, because you typically would assume in the graph setting, you can say, if your graph is actually sampled from some kind of manifold, you can show that the Olivier-Ricci curvature under some conditions actually converges to the Ricci curvature of the manifold. But for hypergraphs, it's very interesting that at least I don't know of work that really looks into the corresponding smooth object that one could get. Maybe there is no such smooth object, right? But for instance, you could use curvature, or you could use hypergraph curvature to assess different simplicial complexes and assign it a curvature value. And then you would be a little bit in the realm of something like Forman-Ricci curvature for these combinatorial complexes. But yeah, it remains to be shown what we can do with some kind of Olivier-Ricci curvature on these type of data structures.
Okay, thank you. So if there is nothing else, I just again thank you very much for this very inspiring talk. Thank you.
Thank you very much for having me. It was a pleasure.